To jeszcze co dajmy z 2 minuty, ale już sobie trochę.
Mogę puścić na koniec ołeka?
Tak, to już z tego tyle. Okay, so we will start with the last session of today with presentation by Tomasz Chmielewski, President of Management Board of Livecare Technology, the partner of neurorehabilitation. And so please start.
Very strange. Polish company based in Łódź, and that's why I'm really very happy that I can support this conference, which is really extremely important from the point of view what we do. It will be less about research and development. It will be rather about bringing products and ideas to the market, because we produce and distribute products for supporting neurorehabilitation. The company is since 2009 also the alumni of International Faculty of Engineering, technical university. So that's a big honor for me to be here together with you. So Igor, thank you for invitation, and I hope that maybe in future I could help to bring some products or services to Polish or European market, because we do that, and I would like to tell you what we do. So first of all, as I mentioned, we are the manufacturer. We have a factory in Łódź. We employ 70 people. We have own research and development department, employing four staff. Sales team in Poland, Czech Republic, and Slovakia, and we export our products to more than 30 countries, even to such faraway destinations like South Korea, Singapore, Australia, Latin America, and to major European countries. Within our products, is standards. These are the devices that go from the sitting or lying position to the standing position for all cerebral palsy and neurological diseases. These are rehabilitation chairs, electrical seat-to-stand devices, strollers, wheelchairs, tricycles, and car seats, all for disabled. So all products are medical devices, CE marked with respect to MDR, so the European law. So even tricycles that looks like a bicycle or tricycle, but they are all for disabled people. So we produce it in Łódź. This is now
I received information that we are not sharing the presentation. So sorry for that. Is it okay now? No, is it okay? Okay.
We are online, right? So all these devices that you can see on these pictures, we produce in the factory in Poland, close to Gillette at Kinia, in Lodz, in special economical zone. These are the examples of product we produce, but we also have a lot of products for neurorehabilitation, because all these products rather support the daily life of CP, stroke patients, and all neuro disease are less with active rehabilitation. It's rather the support to ease them the daily life, so they cannot move alone, they cannot stand. Their sitting position is very unstable because the muscles are very weak. So all these devices, the main aim of these devices is to support sitting position, to support standing position, because for example, CP patients or another neurological patients cannot stand on their own. But we also have the second leg of our business, where we have a lot of robots which support active rehabilitation. And the first example of such a device is Prod Robot, which is automated gait trainer, as an active medical device designed for the rehabilitation of lower limbs of patients with gait dysfunction. So all patients the examples of diseases where this device can act is stroke, paraplegia, Parkinson's, cerebral palsy, muscular diseases. And this project is an example of our cooperation with startup market, because it was developed and invented by the small team from Krakow in Poland. And at the end of the project, we started to be the exclusive partner for this startup for distribution, to distribute the product in Poland and on a few European markets. And we are still together. So it's the cooperation started seven years ago, and we still are the partner for product. The second strong brand which is in our portfolio is a brand NeoFect. That's it's one of the biggest worldwide brands that are within neuro rehabilitation and hand therapy. The company is based close to Japan. It's from South Korea. They have also branches in United States and in Europe, and we are NeoFect's exclusive partner for Poland. And they have smart gloves for neuro rehabilitation. That's the main top seller, and it looks like this. More techniques because we had a lot of research. So that's the product that entered the market. Wireless, lightweight, with elastomer material, 9-axis movement sensor, and with real-time biofeedback device. This is supported with a lot of games similar like Neuroforma that was introduced 2 or 3 speeches before. So you have a lot of games. You move your hands, and the glove is on your hands, and all movements are on the laptop, on the computer, on the screen. If you move, you can play. You can twist something. You can throw a ball, and this kind of games that should support active rehabilitation. The main goal, of course, is always that the patient should rehabilitate, but it's also that the rehabilitation should not be boring, and should engage the patient. So it's more. So he wants to train, and he wants to come back, because that's one of the most important points for home rehabilitation. This gloves is very popular in United States, where it's funded by the public sector, so the patient can take it to home and use it, and National Health System of United States pays for it. So this neurorehabilitation looks different in different countries, mainly because not the technology is different or the patients are different, but in most cases it depends on National Health System insurance systems. So it's important who pays, who wants to pay, and for what they want to pay. So, for example, in Poland, you cannot take such a glove to home and have this therapy at home. In United States, you can. In Germany, probably also, but it differs. It differs country from country. Next brand that we have in our portfolio, which support the neurorehabilitation, is Lightgate. This is the most popular system also in the United States. It's American brand. So system of lifting and supporting the patient in a standing position over the treadmill or over the underground. This system is so popular that 80% of American hospitals use that. It's like a one choice system for America, for example. Of course, not so popular in Poland, and encourages postural stability and correct posture. So these systems are used to train walking, and to be able to the physiotherapist doesn't have to lift the patient, and he can correct the body posture. He can correct the gait, walking pattern, and so on and so on. At the last but not least, this is the set of systems that I wanted to concentrate more, because we started to work with these therapies and this technology 5 years ago, and we have more than 200 implementations in Polish rehabilitation centers and hospitals, and this is mechanostimulation for rehabilitation with low and high frequency. I will explain what does it mean. In general, it's these are vibration platforms. Vibration platforms, so platforms that vibrate very, very, very fast. You will see it here. Can you see? You can see. So you stand on a vibration platform. This is German. This is German brand, and this brand and technology is so popular that I can maybe it's like a news from 1 month ago. Our Polish National Chamber of Physiotherapists decided to include mechanostimulation in the national courses for physiotherapists as a method of therapy. We worked with this technology for 5 years, and after 5 years, we convinced Polish National Chamber of Physiotherapy. They really like it, and what is it? So it's a very fast movement, similar to walking. That is why it's very safe, because it's not the movements of the platform are not vertical like this. Although you can find this kind of platforms on the market, but not in this Galileo trap. It's like a walk. So it's side alternating movement with low or very high frequency. What this frequency means? It means that, for example, this is 25 muscle contraction per second, or you can make a 1,500 muscle contraction per minute. This is a kind of technology of training which you can make a goal very quickly. There is no faster possibility, and what's the most important, it's for many patients that cannot train. So it's, for example, it's good for oncology or for cardiovascular problems. So if you cannot have high rate of pulse of your heart, you cannot train. When you step on this platform, within 5 or 6 minutes, you have so many repetitions of this movement that your muscle in 5 or 6 minutes train very fast and very hard. But it's not only for muscles. That's frequency range and therapeutic application. So low hertz, it's like a balance platform, which was presented before by Neurophone. So it's small movement when you can train only balance, mobilization, central communication, passive muscle relaxation. When you increase the frequency, it's a stretching muscle function, coordination, and when you go over 20 up to 40, it's power build up muscle endurance, cardiovascular training, reduction of spinal excitability, so active spasticity. For example, we use it to give some good example that it's more easier to understand. For example, to reduce spasticity. Now we have a lot of introduction to rehabilitation centers, to private rehabilitation centers, to physiotherapists who works with spasticity, because using the platform, it's not only on lower limbs. You can also put your hand on it, and before another trainings, physiotherapists use it to lower spasticity. You need 1-2 minutes of training to reduce spasticity. Of course, not forever, but you reduce spasticity. And for example, for next 1 hour session, it's much easier to do another manual training with a patient. So we start, for example, with mechanostimulation to lower spasticity, or even reduce the spasticity for 1 hour or 2 hours, and to ease the manual training. Where we use it: osteoporosis, back pain, geriatric, urology, neurology, lot, decreased mobility with lung disease, decreased mobility and pain reduction with chemotherapy, children with neuromuscular diseases. Here we have a lot of introductions in Poland. Yesterday, Centrum, tell the name of the Polish. Yesterday, the order did for two units. Centrum Zdrowia Matki Polki, for example. So that's one of the biggest child hospitals. Ordered yesterday 2 units of this mechanostimulation, and a lot of sport injuries. So that's And to sum up, this one of the key technology that we are really happy within neuro rehabilitation sector. Main benefits of Galileo therapy: it's a stimulation of many muscle groups at the same time, provides correct physiological neuromuscular activation with no electrodes, and quick step versus electrostimulation. So you don't have to put any electrodes, because you could probably reach the same or similar effect, but you don't have to do that. Much cheaper, because electrodes are only for one patient and you have to exchange it, for example. Galileo trains high muscle power with low cardiovascular influence, rather than resistant exercise. So it's not a fitness. So you are not tired after this, because it's short. It activates your muscles, but it doesn't make you it doesn't make you tired. That is why a lot of hospitals use it, because the patient, for example, will not have a heart attack when, for example, it's not a bicycle. If you put your patient on a bicycle with some diseases, maybe he will have a heart attack, because he will be tired on a bicycle. It's not this case. You can train faster and no risk of high pulse of blood. So Galileo therapy provides a high repetition. That was in a short time. It was already mentioned. Combines voluntary movements with involuntary muscle contraction that leads to much higher muscle activation. That's a point, for example, for sports. The sports we for example, with our machines, it's also really a Polish name. The biggest Olympic center in Spała, where all athletes prepare for games. They use our Galileo therapy for sports athletes, because as I mentioned, much faster in a very short time, and spasticity. The last point I mentioned before. So thank you for your attention. I'm really glad to be here, and I hope that more and more ideas and research will come to the market, and maybe we will in future be part of this transfer of technology from Polish universities, Japan, to the market, because with our position right now, we have really, that's a good point to introduce a lot of interesting technology to Poland and European market. And I hope that it will be together with Polish with Technical University of Łódź. So thank you very much, and if any questions, please ask.
Do we have questions? I know that some of the devices that Professor Morita does are kind of similar.
Yes, thank you very much for your very interesting presentation. I have one question about Galileo therapy.
Which therapy?
Galileo therapy.
Okay.
What parts of body is spasticity reduced? Or
we have practice especially with this part and hands.
Hands and the
Yes.
lower.
Yes. For example, if you put a hand, on yes, and you will reduce plasticity in a hand, and then physiotherapists continue manual therapy, for example, during the 1 hour session. But they first use Galileo as a start point to reduce spasticity. We have a lot of research. If you and publications. That's a technology that has more than 300 or 400 publications. That's it's more than 20 years in Europe. in Germany, Austria, and Switzerland, where the Galileo was started, they have more than 5,000 implementation to medical sector, and the number of research and publication is really amazing. So if you are interested in, especially in spasticity, it's not a problem. I can share with you with a lot of publications how to reduce spasticity with mechanostimulation.
Okay, and I have one more question about the frequency of the vibration. What frequency of vibration does spasticity reduce?
I don't remember. I will check it. I will let you know in later session. I have to check because I don't sell this technology day to day. So, but it's not a problem. I will check it and I will share with this knowledge later on today.
I actually had a question about the way you said that for different countries there are different rules, but you mean the rules like on the level of financing, or the rules that they actually prohibit, for example, taking the device home?
No. That's a case of not prohibiting. As far as I know, in Europe, you can everywhere use nearly the same devices in public sector or private rehabilitation centers or at homes. But a problem is finance. So in Poland, in rehabilitation, as for now, there is no one procedure. I don't know the procedure that allows to take the device on a regular basis to home, and that for this service Polish national health system pays. It's not like this that you go to the doctor, you have a prescription, and you can come back home with, for example, any rehabilitation device. Of course, you can try to buy this rehabilitation device, applying for special funds, but it takes months. Sometimes you have 20%. You have to pay 20%, for example, for a device, and you have to write a letter and convince the committee, the jury, that this device is really important, and you require this device to take it home, and after a few months you have positive or negative answer. Is it accepted or not? So there is no procedure. Doctor, you are sick, so it should be fast, especially in rehabilitation. After stroke, the rehabilitation should start as quickly as possible. So you should go to the doctor, and you should you should first, for example, you should have rehabilitation in hospital. Then when you come back home, the good therapy should be at home. So you should take it home. There is no fast track. There is no any fast path to do that, because waiting a few months when you apply for public funding and waiting for response from PEFROM in Poland, it takes months. So it's not the case. In USA, for example, for this NeoFact, they have financing that they rent it. So it's like a prescription. You come back home with smart glove, and they rent it, for example, for 1 month, 2 months, or 3 months, and then you give it back. So that's the main problem, financing, as usual. So money is always a problem, especially in health rehabilitation sector in Poland and in Europe. Of course, we are not on such a bad position because there is some financing for privates, for individuals. But it's still not like in Germany, USA, or I don't know how it looks like in Japan. That's quite interesting for me to ask you about it later. But we can hope that it will be better and better.
Okay, thank you very much. So thank you. Okay, so the next presenter will be from Łódź University of Technology, miniature orthopedic measuring device, NaviFast 6D. I understand that the presenter will be Piotr Szachowski. Later, sure.
Afternoon. I'm Piotr Rakowski, PhD at Wrocław University of Technology. My team that works on servi. It's a device for orthopedic measurement during free replacement surgery. And I'm going to tell you some interesting facts about the device. But firstly, I have to showing you the information that currently there is more than 2 million operations of hip replacement annually in only Europe and the USA, and that number is only going to increase. And unfortunately, more than 10% of such operations end up with leg length error exceeding 10 millimeters, which causes further complications and is the main cause of lawsuits in the United States of America based on medical practice error. So the reason for that situation is that there is no measuring device that would enable the surgeons to measure during the operation precisely the change of length of the leg. So the surgeon themselves have asked us to develop such a device and set us a goal to invent the measuring device that would meet all their expectations, which are the small size, short time of performing measurements, ease of usage, and disposability. It was a difficult task, but Professor Leszek Podsetkowski, the leader of our team, came up with an idea of using MEMS accelerometers in a very innovative way to perform measurements of displacement. The idea is that we build a articulated arm made of 7 links connected with 6 rotary joints and equip each link with one 3-axis accelerometer, so we can detect the angular position of each link related in relation to the Earth's gravity field vector. So by measuring that value, we can further determine the position of each angular if joint angle, and this gives us ability to calculate the distance from the base of the device to the probe. So we use the Dynamit-Hattenberg notation system for that operation, and thanks to that, it gives us the opportunity not only to measure the elongation of the leg, but also offset and related angles. The significant limitation of that technology of conductive measurements is that none of the joints axes cannot be oriented vertically, because in such a situation there is no possibility of detecting the alteration of angular position of the three-axis accelerometer. This problem can be mitigated by using the kinematic structure that provides us, eliminates the risk of such a situation. Another challenge was to invent a fastening system which would enable us to attach the measuring device to the bones of patients. The most problematic part is that the bone is heavily degraded by, for example, osteoporosis, and does not provide film support for the device. It results in measurement errors heavily visible in other measuring devices. We managed to invent such a fastening systems, but for today I cannot show you these devices yet because it's going to be patented. However, I can tell you that the measuring method by itself is patented and legally protected in Poland, Europe, United States of America, and Japan. Our project is quite advanced, that we already achieved level 7 technology readiness. Level 8 will be achieved in 4 to 6 months. We performed with the help of surgeons several tests in real conditions, which turned out to be successful. And we created the final design of the device. And our next goal is to commercialize the NaviFast 6D. Apparently, we have a few significant advantages over our device. For example, our device which will be much more accurate and faster and easier to use, because to perform all the measurement procedure, we use only 2 buttons, and it's very easy to learn how to operate with that device properly. Also, the cost for the end user will be much lower in comparison to the currently available devices, which will enable us to provide the measuring device to large number of hospitals and therefore patients. The commercialization is planned to occur in late 2023, when we will achieve all the requirements set by the certification procedure. And that's pretty much all. I hope you find this presentation interesting, and I look forward to hear your questions.
Thank you very much.
So in what orientation do you have to measure?
You mean the patient is he lying or back or on a side? Because there are,
I understand it's something like kindness, yes?
yes, exactly.
And in which orientation do you have to measure?
It's basically the markers we put on a bone provide the defined range of positions the probe and the base will be oriented. So the arm, regardless the position of the patient, starts the measurement in a predictable position. In both cases, when the patient is situated lays on his back or on a side, and therefore the range of motion is predictable, so we can assure none of the axes will exceed will become oriented vertically.
Because I'm asking about the orientation relating to Earth's gravitational field.
Yes.
So can you measure any orientation or one specific orientation?
There's this limited range of orientations in which this device will work, and it's fully designed to meet requirements of any position the patient will be situated.
Yes, sure.
Okay, so no matter what the position the patient is in, you have to take your tool vertically, basically.
Yes. The markers provide the support for the device in such a way that this requirement is met.
Okay, thank you.
Are there any other questions?
Hip replacements.
Yes.
This is also the device that will measure the hip dislocation.
When there is a dislocation, there is no set kinematics. Everything is loose, right? Because the femur is no longer attached to the pelvis, right?
For cerebral palsy kids, a lot of hip dislocation. And the orthopedists measure the hip dislocation just to check and evaluate if the surgery should be carried out or not. Some parents decide to carry out the surgery or not. But the hip dislocation should be measured. Is it a device also for that or not?
Because it requires the surgery, right? Dislocation can be detected via röntgen, right? And it's cheaper, faster, and safer to make a röntgen than to open the patient. It's designed specifically for that purpose. To measure
Replacement.
yes, to measure the alteration of leg length and offset during hip replacement surgery.
Okay, so thank you very much. And we will have another presentation from which University of Technology, this time about the device I was co-designer. So software platform for Przypominajka hand rehabilitation device towards Przypominajka 1, 2, 3. And the presenters, we will have two presenters, so Maria Bogdan and Katarzyna Łódź be presenting together, right? Hopefully not in the same time.
Włączyła kamerka, nie widać agenta? Nie, widać. So, good afternoon. My name is Julia Bogdan, and this is Katarina Guć, and we are going to show the presentation regarding Przypominajka device. In the beginning, we will explain the idea of Przypominajka and what is the role of motivation in this project. Further, we will briefly talk about different versions of Przypominajka, and at the end, we will present the future goals and plans for the further development of the project. So Przypominajka is a device supporting rehabilitation for patients with spasticity. It consists of two elements. First one is a glove-based device connected to application via Bluetooth. And the application was developed with the usage of MIT App Inventor. Currently, the rehabilitation of patients with spasticity focuses on lower limbs. However, the upper limbs are crucial as well. The rehabilitation process for people with spasticity, the upper limbs rehabilitation improves their feeling and motion, and that improves their quality of life as well. The main goal of Przypominajka is to remind patients about the time of exercises and guide them through the whole process. So why the motivation is crucial in this project? As it's known, the motivation results in regularity, what causes the improvement of the result. So our aim is to find a way, how can we motivate patients to regularly perform exercises? Our idea is to create some visual stimulus to increase engagement and attention. The first idea is to reward patients with the stars after collecting some certain amount of points. The other idea is to provide a constant feedback about the user's activity or lack of it. The idea is to fix time to give a user some sort of like a visual representation of the activity. In our case, we came up with idea about blocks. So a block corresponds to the commitment that the patient gives while performing the exercise. So the bigger the block, the higher the commitment occurs. The last idea is to implement a game. The glove placed on the healthy hand would function as a controller to move the other hand that will be rehabilitating with the other device. This way, this feature we can implement in the game to, for example, omit obstacles or collect some objects that are displayed on the screen. And as it was said before, Przypominajka version 1 consists of two elements, and the application shows the display of exercises that are supposed to be performed, and more importantly, it gives information about the duration of exercises and breaks between them. And due to received feedback, some improvements were implemented in the application. One was about the display of the images. Patients had some problems with understanding the exercises. So it was better shown how to position the hands and how to keep proper body posture while exercising. Additionally, the STAR scale was implemented to motivate patients. However, due to different level of spasticity for patients, they had problems with collecting the points during the exercise, and not all of them could collect the stars.
And that was unmotivating and frustrating for some of them.
So the other version of Przypominajka is designed to inform patients about inappropriate hand position using accelerometer, flex sensor, and pressure sensor. It is significant to avoid situations when there is excessive bending of a wrist or prolonged pressure on the hand. Therefore, we need somehow to inform patients about this because they don't feel hands, so they somehow forgot about the hand where it is. So it can be very dangerous for them. That's why we can implement few solutions to inform them about this. It can be a visual alarm, sound alarm, or some sort of vibrations. However, each of them comes with certain limitation. Visual alarm may be simply missed. The sound alarm can be muffled when it is, for example, under the leg or something like this. And vibration may not be felt because of the spasticity. But we can combine this solution to achieve better perspectives. So, for example, sound alarm may be fully functional when it's not tackled under the leg or something like this. But then we can use vibrations, which will inform the patient because it will not be felt with a hand, but with the other part of the body.
Przypominajka 1, 2, 3 is a combination between previous versions of the device and the game. It can be characterized by such features as permanent, familiarity, and reusable. So reusable stands for long-term use of the device. The patient has it for a whole duration of the rehabilitation process. Permanent means that patient can wear the device for majority of the day without feeling any discomfort or disruption in their daily activities. Familiarity refers to the knowledge of previous devices. So the patients don't need to learn completely new device. They have some kind of knowledge about the devices, and it's easier for them to adjust for this new version. There are some features that are taken from the previous versions, from Przypominajka 1. It's the reminder about the time of exercises and the guidance of the exercises. From Przypominajka 2, it's the alarm, which informs about the improper position of the hand. And at the end, the game motivates the patients for further engagement and in their rehabilitation process.
So Przypominajka 1, 2, 3 is inspired by a mirror therapy. It is a treatment that focuses on creating the false impressions that both limbs are fully functional, as we are moving a healthy hand and creating a mirror illusion, and patient perceives this as the movement of the unfunctional hand. In our project, we want to put a glove-based device on the healthy hand and cause the same movement on the other hand, this one which is not able to move itself, by using another device that will just move this unfunctional hand according to the movement of the healthy hand. This way, the patient will perform exercise, and at the same time, it gets the impression that this unfunctional hand moves according to his or her willingness. And at the end, we can also controlling movement, we can implement into a game just to diversify the rehabilitation process. So the patient can collect or omit objects displayed on the screen.
Future goals for our projects are implementation of the game into the application to improve the motivation of patients. Additionally, creation of a new version of application in new programming environment. The current one has its limitations. So when we want to implement new functions, it might not be possible. Of course, development of version 2 of Przypominajka and Przypominajka 1, 2, 3. And at the end, we want to test all of those devices among a greater group of people.
So to sum up the presentation, we presented some new possible ways how we can engage and motivate patients to exercise regularly. We also discussed the development of Przypominajka 1 and 2, as well as Przypominajka 1, 2, 3, that is based on a mirror therapy and combines some features from the previous version and this.
And thank you for your attention.
Okay, so are there any questions?
Okay, so I will ask the question. Have you, because you mentioned that the next generation of Przypominajkas, the second or 1, 2, 3, should be more biocompatible or just healthy for the patient? Yeah, so instead of this glove we are putting on the hand, we should use maybe some other materials, for example, with these which are possible to be sterilized or just more hygienic, or easier to keep the hygiene. Have you thought about any kind of these kind of materials? Do you even focus about it, or just
we are more focused on the software? However, it's important to clean the device, so it should be water resistant and
I think it will be wear through whole day. As Maria said, it should be waterproof, but also we should be able to clean that easily, because when you wear it all day, anything can happen. So, and it also should be more comfortable, as it was said that this glove that is currently is very difficult to put on. So it should be easier to, the construction should be easier to put it on.
And about the programming, the software elements. Did you do any tests for elderly patients, or maybe not even disabled, but these people who can have some problems with the modern technologies? So starting with smartphones, and right now there we are giving them the iPad or any other, let's say, modern technology. Have you checked if it's even possible for them to use it, and they will understand how to do that?
We haven't, but I think the best, I think the best idea to implement this sort of application is to make it that when you, for example, take the tablet or things like this, it will automatically open, so they don't have to worry about the use of the device.
Thank you very much.
Thank you.
Okay, thank you very much. We will have another presentation from the My Hand team. And this time it will be a finger straightening device, the alienator. And the presenter will be Natalia Słabęcka. Też jakbyś mogła to tam szerzyć. Jest na Teamsie szeruj, dobra?
Jest udostępniony cały czas.
Że co?
Co jest udostępnione? Ty. Yes. So good afternoon. My name is Natalia Sobenska, and today I would like to tell you about the challenges connected with hand rehabilitation and the prototype of finger straightening device called the Implantator. So the stroke occurs when the blood supply to the brain is stopped, and the most common consequences of a stroke is the spasticity of upper limb, which is characterized by high muscle tension, and the hand with spasticity is often placed in an unnatural position, and the pain can reinforce when the hand is immobilized by several minutes, or when we try to make a rapid movement. Nowadays, there are a lot of robots which we can use in hospital to treat people after stroke, but they mostly focus on bending fingers when straightening them, while the most common mistakes made during stroke rehabilitation is squeezing an object, what reinforce primary grasp reflex. And the second mistake is forceful straightening the hand, and forceful straightening causes that the pain is increased. So because a lot of rehabilitation robots used in hospital are often heavy, expensive, difficult to put on or use by patient, and they focused on bending fingers, I decided to design a prototype which will straighten fingers and will be easy to put on. And now I would like to tell you about the Implantator. So this prototype consists of the moving part, whose task is to straighten fingers, arm support, Velcro straps which immobilize the wires, and material made of jeans with Velcro straps, which is attached to both sides of this device. And this material prevents hand from moving up during finger straightening. The moving part is attached to a platform which moves along two linear guides. And this prototype doesn't have any kind of supply because, first of all, I would like to check if this prototype can do its task. So during testing, a moving part was manually pushed. At the beginning, the moving part was built from cardboard and was rectangle, but this shape made it impossible to straighten the thumb. So the shape was changed to triangular. But after consultation with physiotherapists, we decided that it would be better if hand could, at the beginning, be clamped on moving part. So the shape was changed again, and the final shape is signed by number 3. And this prototype was tested on patient at Dr. Karol Hospital in Łódź, and patient told me that the moving part
should have a slippery surface. So because the slippery surface is the most comfortable for them. So I create some covers made of different materials like cardboard or easy slip made of nylon, plastic bags, and patients were asked to express their opinions, which material suits them the best. And now I would like to tell you how the Italianator works. So the first step is to immobilize the wheels thanks to Velcro straps. Then you have to put patient's hands on moving part. And the first step is to attach material with Velcro straps to the both sides of the device. And then you have to push moving part forward until you feel medium resistance from fingers. Come back with moving part to the starting point and push it forward again. So on this video, you can see patient with a degree of spasticity equal to 1, and there were no problems with straightening his hand. How to make it post. Okay. So in case of patient with a degree of spasticity equal to 2, there was no problem too, like in case of patient with degree of spasticity equal to 1, but the now I can continue. So the problem appeared in case of patient with a degree of spasticity equal to 4, because his hand rotated and couldn't be straightened. And Velcro straps in this situation were not be able to hold the hand, which is very tightly clamped on moving part. And the forces which I used were not able to overcome the resistance of the hand. So my result is that in case of patient with a degree of the spasticity is not greater than 2, the prototype can fulfill its task, but not in case of patient with spasticity, a degree of spasticity equal to 4, and the device is too large and heavy, so patient weren't able to use this prototype on their own. And all patients told me, give me a feedback that the cover made of easy slip is the most comfortable and suits them the best. So this prototype can be useful in case of a post-stroke patient, but only when they have a degree of spasticity equal to not greater than 2. And the Velcro straps, which immobilize the wrist, should be soft and wide, because at the beginning, the straps was thin, and patients told me that these straps weren't comfortable because this patient often had a swollen wrist. And my future plan is to develop a prototype which will be not as heavy as the Italianator and will be smaller, as the patient could use it
on their own. And maybe I will use for this purpose soft actuators, which will cause that this prototype will be light. Thank you for your attention.
So are there any questions?
No questions.
For the discussion that we could do it to this push without any other physiotherapists.
Yes, but it's pointless to make a robot if the device can fulfill its task. So this is why I didn't add any supply. Okay, so I will ask one more question. Because you mentioned that there were different shapes of this element where the fingers, which should straighten the fingers, and you changed the shape quite a bit. And as you showed on the video, that for the level higher than the second level of the spasticity, it was impossible to straighten the hand. Have you thought about maybe changing this element a little bit more? So maybe it will be helpful, or is it completely impossible because of the forces which appears in the spasticity?
I thought about changing the shape of moving parts, but the forces of hands of patient with the degree of spasticity equal to 4 are too big that I can try do it, but I think that the moving part, even if I change the shape, it won't be able to straighten the hand.
Okay, thank you very much.
Thank you.
Okay, thank you very much. Last presentation of this will be presentation by Tomasz Smash, modular soft robot test and measurement system. This is also connected to our project about hand rehabilitation.
Okay. So welcome everybody. I'm Tomasz Strasz. I'm here to tell you about the modular soft robot test measurement system we developed in our project. So first of all, I should probably tell you about what are the soft robots. So the idea is that instead of having a rigid construction of the actuators, we can make them from flexible material and maybe control the application or to the person operating it. So we are doing some experimentation on such devices in our time, and we thought that it would be quite handy to compare them between themselves. So of course there is a need to measure force such devices and deflection, and there is some lesser obvious things such as reliability. So we should know if we want to apply such device in any real-world application, how much pressure can we push reliably into such device before it catastrophically destructs itself, or even if it will be sustainable for it to repeat many operational cycles. So we it's quite a broad topic, but we had to start somewhere. So we started with such a simple device that just shortens itself when it's actuated. Actually, on the image, there is shown an example of the actuator that gets shorter when there is a vacuum applied, and it's made from foil. And there is some internal structure inside, as you can see. So the whole setup is divided into three parts. There's a PC application, there's ESP32 firmware and the control board, and also there is a test setup as a whole. So the test setup consists of all the required mechanical parts. So there is a spring that loads the actuator that allows it to work like it would in the real world scenario. And there is also a camera that allows us to track what happens with the actuator. There are also required sensors such as strain gauge beam that measures force exerted by the actuator, and there is also a laser displacement sensor that measures how much the actuator changes in length. And that because of the actuation that is achieved to pneumatics, there is a whole pneumatic system that is powered by air pump and regulated by air valves. There's a reservoir that allows us to control the flow rates, pressures, so to say, and there is a pressure sensor that is used to compare the set value with actual value of the system. So everything comes together inside the two. There is actually one control module. There's an extension module that allows us to plug in high-powered devices such as the air pump, and there is mainboard that connects to sensors and has the controller built in, and also connects to the PC, where the dedicated application communicates with that board and also with the webcam mentioned earlier, and collects all of the data over the course of the test session, which is just to go towards that pressure point, stay there, and go to the next pressure point when it's required. So there is an example of such cycle. So the application set the pressure. Our board regulates the pressure to the required value, and it sends the information to the PC application back that the pressure, not the error, is small enough, let's say. So here's an example of recording from the tests in progress. And there are some graphs that are collected from the device, and actually this is the same recording that the data is collected from. As you can see, there is quite a lot of noise in the measurements, but part of it comes from that this is a lot of points. So this is data collected over several cycles. And also there is some noise introduced by our measurement setup. There's also quite an interesting way to represent the data. So to observe both the force and elongation of the actuator at the same time. So it's easy to visualize changes in the actuator, for example, if it stretches over time or if it doesn't achieve the force, and easy to see that on such plot. So, in the conclusion, we made the setup, it collects data. It's not perfect by any means, so we know already that there is some slack in the system, because there is a lot more non-linearity in the deflection measurements than in the force measurements, and it shouldn't be the case because of the spring that loads the device. And also there is a lot of noise that I mentioned before, but I think that is just an unfortunate complication resulting from the high noise of the ADC converters in ESP32 and quite a large range pressure sensor. So what we will do next with this? We have to replace the sensor or apply some external analog digital converter. Then we can also fix the mounting system because there is some slack in there. And we can then test the actuators, try to compare data collected both with the previous data and hopefully some simulational data. And also, if we know then that everything is well, we can then extend our test setup to measure different kinds of actuators, because soft robots are famous for achieving many complex movements, and shortening one is quite boring one, I would say. So we can talk about bending actuators or twisting actuators, for example, and only do all that when we are done, I think, with that idea. So thank you for your time. Are there any questions?
Are there any questions to this station? Professor Molina.
I have one question about the noise. There are many noises in the force pressure. The noise affect the result you mentioned.
Well, it affects the results in two ways, because first of all, when we are seeing the plots of the values versus pressure, we are referring to that noise for one, and also that noise also affects the pressure regulation. So the pressure tank itself has some fluctuations to it as a result of the regulation.
So how do you improve in the near future?
I think I can improve it in several ways. Just most obvious is just selecting the pressure sensor that has the lesser range. So we have, I think, 16 bar of range. That is quite insane for the soft robots. But if you would select, for example, a sensor for 2 bars of range, we can decrease the noise 8-fold, or noise influence 8-fold. And the one more way we can improve the noise performance of the system is to replace the analog to digital converter for something less noisy, or mostly something less noisy, because we have enough of resolution.
Thank you.
So any other questions? This was more on the technical side, but the point is that we, for example, the work that we showed before, so Balonikotron or Natalia's Dalia Nator could use this kind of actuators, and we need to test them. This was the point of this. Okay, so thank you very much, Tomasz. This was the last presentation of today. As this is the, I would say, more public part, I would like one or two words from Professor Molina, just to finish this day.
The ocean. Okay. Okay. I'd like to close the first day of this workshop. I would like to express my gratitude to Dr. Igor Zurotsky. Thank you very much. And I appreciate to you for joining the conference and joining the discussion time and giving presentation. Thank you very much. I think this workshop was very fruitful and meaningful, productive workshop. So I believe, I think, I also think we were able to share the knowledge and information and to promote the mutual understanding Poland and Japan in the medical rehabilitation and engineering, and then we enhanced the cooperation. And the last time in 2019, I told you again that I would like to close this session with Japanese ceremony, Japanese performance called Ipponjime. Called Ipponjime in Japanese. It's very easy. I told you that I will teach how to do it. It's very easy. Okay. First of all, I say yo. It's like a kabuki, Japanese performing art. Okay. So after that, you should clap your hand loudly once. Okay. Okay. Are you ready? Okay. Yo. Thank you. Thank you very much.
Thank you very much. So with this, we conclude. Thank you very much for everybody for attending.